Okay, this is the beginning of the module on single user wireless communications. And so this is where we're going to talk about all the special techniques that people use to design communication systems that operate over the wireless channel. We make the distinction here right at the beginning that this is single user wireless communications. So we will only be considering a single transmitter transmitting to a single receiver. Obviously, there are also multi-user communication systems, things like cellular networks, but that will be considered in a separate module. So, as I said, the goal of this module is to introduce you to some of the special techniques used to design wireless communication systems. And there are two very important perspectives that we can take when looking at the design of wireless systems. The first, the diversity perspective, is perhaps the more traditional perspective. It's the perspective that people originally took when the very first wireless systems were being developed. And the second perspective, the spatial multiplexing perspective, is something a little bit more modern and a little bit more recent. So we have seen in the module on the wireless channel that the multipath channel causes unwelcome distortion that must be mitigated or taken care of somehow. And the idea that we need to sort of take care of or minimize the distortion of the wireless channel leads us to the use of something called diversity techniques. The second perspective is that the wireless channel, the multipath channel, actually has some useful properties that we can exploit. So we can use some of the wireless channel properties to our advantage. This leads us to the use of what's known as spatial multiplexing. And as we will see, we're going to use the properties of the wireless channel to actually increase the throughput of our wireless communication system. So a good place to start when discussing wireless system design is to derive the probability of error for BPSK over a Rayleigh channel. Now, basically what this derivation is going to show us is the performance degradation caused by Rayleigh fading distortion. And this is going to lead us into the whole mindset that fading is bad and that we need to remove it or eliminate it somehow, which is going to lead us into the discussion, nicely lead us into the discussion of diversity techniques. Now, as I mentioned in the previous slide, this is sort of historically how wireless systems design evolved. But the notion that the multipath channel is always bad is now slightly out of date because, as we'll see when we get into spatial multiplexing, the properties of the multipath channel can in some cases be good. So let's start by considering BPSK transmission over a flat Rayleigh faded channel. And just to introduce some notation, during symbol interval I, HI represents the channel. Now, we know that a flat fading channel has only a single tap, and HI represents that tap. H is a zero, for Rayleigh fading, H is a zero mean complex Gaussian random variable with a unity variance. Now, this unity variance is worth mentioning because it basically means that the average gain of our channel is 1. Now, we know from the wireless channel module that in addition to sort of small scale fading effects, the channel also has large scale effects which serve to attenuate the signal. And essentially what we're doing by setting the variance of H to unity here is we're neglecting that attenuation. And we'll see later on when we plot our bit error rate how we kind of get around that or how we deal with that. But assuming a channel gain of unity is very commonly done when conducting mathematical analysis or even simulation of a wireless system. X represents the transmitted BPSK symbol. We're using baseband notation here, so it's equal to plus or minus the square root of the energy per bit. N is the zero mean complex Gaussian noise corrupting the symbol X. what we're going to do in this derivation is assume something called a coherent communication system. Now, to explain what this term means, we know that the Rayleigh fading process will corrupt not only the amplitude of the transmitted symbol, but also the phase. Now, this is a big problem for phase shift keying systems because phase shift keying systems obviously use phase to transmit information. And so if the channel distorts that phase, essentially makes it impossible for the receiver to recover the transmitted information. Now, this is true if the receiver has no knowledge of the distortion caused by the channel. And when the receiver has no knowledge of channel distortion, it's what's known as a non-coherent communication scheme. However, if the receiver does have knowledge of the distortion caused by the channel, we have what's known as a coherent communication system. And this is what we're going to assume in this derivation. How does the receiver get knowledge of the channel distortion? Basically through the transmission of a known sequence of symbols, either as some sort of training symbol sequence that comes at the start of an information packet, or perhaps as some sort of pilot signal that is transmitted in parallel with the information. And basically, the receiver uses that known sequence to estimate the channel and then use it to help in the recovery of the transmitted information. And so, before we get into the derivation, it's useful to look at a simple block diagram of the transmitted symbol. And so, here we have the transmitted information symbol X going through our channel, and the channel response is H. Now, the output of the channel is the convolution of the input and the channel response. However, because the channel is only a single tap in the flat fading case, essentially what we have at the output is the information symbol multiplied by the complex weight of the channel. We then have our additive noise and our received, the signal then that the receiver has to deal with is equal to the information symbol multiplied by the channel plus the additive noise component. Now, the next question we need to ask ourselves is how should the receiver deal with this received symbol? Now, in many ways, this is very similar to the received signal that we had when we looked just at the additive white Gaussian noise channel. We have some received information symbol corrupted by additive Gaussian noise. And in that case, we saw that the best or the optimal way to deal with the transmitted information or with the received information was to use the matched filter. And the matched filter would essentially convolve the received signal with a flipped and shifted copy of the transmitted symbol pulse shape. And so basically we use exactly the same receiver structure in a wireless system. So when in this diagram, when I represent all of the transmitted symbols and the received symbols as essentially one complex channel or one complex sample per symbol, essentially implicitly what we're assuming is that basically at this point in the receiver, we have a matched filter matched to the transmitted symbol pulse shape, and that these samples we have here are basically the samples that we have at the output of the matched filter. And so that's fine, except that now we have this extra wrinkle of having this wireless channel here. Now we can think of the wireless channel really as kind of modifying the pulse shape of the transmitted information. So at the input to the wireless channel, we have our original pulse shape. When it goes through the channel, it gets convolved with the channel response, and at the output of the channel block, we have our original pulse shape convolved or distorted by the channel, and we represent that by x multiplied by h. So the optimal way to handle this received symbol is not to match it to the original pulse shape, but to match our match filter to the distorted pulse shape. So we match it to the shape represented by h multiplied by x. Now, because we are representing everything in this derivation as one sample per symbol, and we sort of have implicitly assumed the pulse shape match filtering portion is sort of built in already, and we're not showing it. Really, all we have to do is add the extra term to handle the channel distortion. Now, in this particular case, because the channel is flat, the channel distortion is just the multiplication of the term h. And so all we need to do is add essentially the effect of that h multiplication to our receiver to make our sort of match filtering operation complete. Now to add some details to that, we'll go to the next slide. So if we want to modify the match filter to include channel effects, basically what we do is we use the same pulse shape match filter output that we would use for the additive white Gaussian noise channel, and we multiply it with the complex conjugate of the channel. And that's basically it. And if we do that, we then have the optimal receiver in terms of maximizing signal to noise ratio for dealing with a transmitted wireless signal. Now, we do a little bit extra in this derivation. Rather than just multiplying by the conjugate of h, we also normalize by the magnitude of h. And the reason why we normalize this by this magnitude is to essentially simplify the derivation. It doesn't in any way change the performance of the match filter for better or for worse. And we've seen that in our discussion of basic communication systems. If you scale the output of a match filter by any constant value, you don't really change the performance. So to be a little bit more complete, the output of our matched filter then, y, so if y is our output sample, is equal to our received signal, x times h plus n, multiplied by our channel term, complex conjugate of h normalized by the magnitude of h. And when you expand out these brackets, you get a desired signal term, x multiplied by the magnitude of h, plus noise multiplied by the conjugate of the channel divided by the magnitude of h. Now, one important thing to point out here is that thanks to this normalization, we haven't changed the variance of the noise at all. So the noise variance remains exactly the same. We multiply by h, but we also divide by its magnitude. And so if you calculate the variance of n, the normalization cancels out the effect of the scaling by the complex conjugate of h. So the noise is essentially unchanged, and we have x scaled by the magnitude, the Rayleigh faded magnitude of the channel. So now, using this received signal model, we can derive the bit error rate for the received BPSK signal. So now, if we think back to our discussion of sort of basic digital communications, we know that if we have a BPSK system with amplitudes of plus or minus a, the probability of error in the additive white Gaussian noise channel is 2a squared over n naught square root all inside the Q function. Now, essentially what we have in the wireless channel, if we look at the equation up here, is that we have our additive Gaussian noise, variance is unchanged thanks to this normalization. And so we kind of have BPSK, our original BPSK symbol, but it's just scaled, right, by the magnitude of the channel. And so our received signal amplitudes then are equal to plus or minus root EB, just like they were before, scaled by the magnitude of H. And so if we just take these amplitudes and substitute it into the probability of error for BPSK, we then get I'm going a bit crazy with the lines here. We then get this expression at the bottom of the screen. And so this is the probability of error for a particular value of H, right? So we know that H is a random variable. So if we took a particular value for that random variable, a particular realization, then this is what the probability of error would be. So on the previous slide, we derived the probability of error for a Rayleigh faded BPSK signal for a particular fading value, right? So if we took a particular realization or a particular value for that fading random variable, we could plug it into that bit error rate expression and get a probability of error. Now, the problem with that is that we know that the Rayleigh faded random variable takes on a whole bunch of different values. Sometimes its value is quite strong. Sometimes it can be very weak if the channel goes into a fade. And we need to come up with some way of dealing with this. And the standard way is essentially to present an average bit error rate. So we basically take that bit error rate expression and we average it over all the possible values of the BPSK fading channel and come up with an overall average bit error rate. And so we can think, so to sort of move towards this, the first thing we're going to do is do a little bit of sort of notation simplification. So I'm going to use the random variable v to represent the magnitude squared of the fading channel, right? And if we go to the previous slide, we can see here that the probability of error is a function of the magnitude squared of the Rayleigh fading channel. And so we can think of this bit error rate expression at the bottom of this slide as essentially a conditional expression for bit error rate. Given that the random Rayleigh fading channel holds a particular value, we can figure out what the bit error rate is for that particular value. And so if we, on this slide, to simplify our notation, let v represent the magnitude squared of the channel, we can express the probability of error conditional on a particular channel value v to be equal to q root 2v EB divided by n naught. And so this is a conditional probability of error expression. Now, in order to get the overall average probability of error, all we do is we take this conditional probability of error and average it over the distribution of v. For the Rayleigh faded channel, the magnitude squared of h is going to be exponentially distributed. And so what we do is we take our conditional probability of error expression and we average it over this exponential distribution. And you do that by multiplying by the PDF. This would be the exponentially distributed PDF. And then integrating from 0 to infinity. Actually, usually it's from minus infinity to infinity, but there's no such thing as a negative value for v in this particular case. So we integrate from 0 to infinity, and we get an overall average bit error rate. Now, if you work through the mathematics and do a series of simplifications, you come up with this nice compact expression here. And so this is the probability of error, the average probability of error for BPSK when you average over all the values of the Rayleigh faded channel. Now, I'm obviously not showing the details necessary to do these simplifications. You can find these details in most communication systems textbooks, wireless textbooks, as well as journal papers. And this is in no way to minimize the importance of these mathematics. In many cases, or actually there are many sort of journal papers written in communications theory that essentially make the contribution of just solving a really, really hard integral to come up with a bit error rate expression. But it's not useful for me to show you those details in video form. Like I said, you can look at most communications texts and you'll see those details there. So now that we have our expression for the probability of error for BPSK, we are ready to compare BPSK performance over the Rayleigh channel with BPSK performance over the additive white Gaussian noise channel. And this is what this plot looks like. So here we show the probability of bit error versus signal to noise ratio, average signal to noise ratio, or EB over N naught. The solid line is the bit error rate for the Rayleigh channel, and the dotted line is bit error rate for the additive white Gaussian noise channel. And we can see a couple of things. First of all, not surprisingly, bit error rate, or the probability of bit error, is higher or worse for the Rayleigh faded channel, and this is due to the extra distortion caused by the fading. And so basically we're adding the same amount of noise to the two systems that we're comparing, but the wireless system has to contend with the extra impairment of the Rayleigh fading. The second very important thing to observe on this plot is the shape of the curves. So we can see that in the additive white Gaussian noise channel, as you increase signal to noise ratio, you get the familiar waterfall curve shape, and you get quite a steep plunge in bit error rate as you increase your EB over N naught. And so this suggests to us that if we're unhappy with the bit error rate in our additive white Gaussian noise channel, increasing the transmit power is a reasonably good solution, right? So you increase your transmit power and you get a big payoff. The bit error rate really falls quite quickly. If we look over at the curve for the Rayleigh faded channel, we see something very different. So rather than having a waterfall curve shape, the bit error rate curve is essentially linear. It's essentially a straight line, and the slope is not very steep at all. So we can increase the signal to noise ratio in our system by increasing our transmit power, and we can add dBs and dBs of transmit power and not see very much of an improvement in our bit error rate. So this tells us that increasing transmit power in a wireless system, if we're not happy with our bit error rate, really isn't a very good solution. We need to come up with some other solution. And this is going to lead us into the discussion, our discussion of diversity. Now, one final thing that I should mention in this plot is with regards to the unity channel gain that we assumed for our channel at the very beginning. So if you remember, we assumed a variance of 1 for our Rayleigh faded random variable, and we added no large-scale channel attenuation. Basically, when somebody is trying to use this type of bit error rate versus to signal to noise ratio plot, you would essentially do a link budget calculation that use channel attenuation to figure out what your received average EB over N naught would be. And then you would, so let's say you have a certain transmit power, 1 milliwatt, you have a certain received, or you have a certain large-scale channel attenuation, you have a certain level of thermal noise, and when you do that calculation, you determine that just due to large-scale channel effects, you get an average received signal-to-noise ratio, let's say of perhaps 8 dB. So what you would then do is take that 8 dB, go up on this plot, determine what your bit error rate is, and use that as your system performance value. So basically, we don't include large scale excuse me, attenuation in our derivation. We assume that the system designer would add the large scale attenuation later on when using these bit error rate plots to figure out what their average receive signal to noise ratio is, and then what their average bit error rate would be.